So we'll take a few minutes in this video to check out problem number 19. This is from section 3.7. It's an optimization problem. It's one that gets pretty involved. If you read what we've got here, it says the city is going to build a new section of highway to link an existing bridge to an existing highway interchange. The interchange lies 8 miles to the east and 10 miles south of the bridge. So if the bridge is here, 8 miles east and 10 miles south, would put the interchange down here somewhere. So we know that this is 8 miles horizontally between the bridge and the interchange, and we know that this is 10 miles vertically between the bridge and the interchange. Goes on to tell us that the first 4 miles south of the bridge, so here's the bridge, the first 4 miles south of the bridge are marshland. So we've got marshland right here, we've got dry land right here. It costs a lot of money, $5 million per mile, to build the highway on the marsh. It still costs a lot of money, but significantly less per mile to build on the dry land. We're going to build the highway in a straight line from the bridge to the edge of the marsh, and then another straight line from the edge of the marsh the rest of the way to the interchange. At what point should the highway emerge from the marsh in order to minimize the total cost of the highway? And so in any one of these optimization problems, what's always good to do is just to kind of make sure you recognize right away what you're trying to optimize. In this case, we're trying to minimize cost. And so what we're going to have to develop here is we're going to have to develop a cost function. And the cost function is going to be pretty easy to construct, but we're going to have to do some geometry that helps us get to that point. And that's where we get into a little bit of trouble potentially. So if it costs $5 million per mile to build on the marsh, we know our cost function is, and I'm just going to have the units of my cost function being millions of dollars. I can carry the 5 million into my cost function. I'm not going to do that. I'm just going to say this cost is measured in millions of dollars. So I've got $5 million times however many miles of the highway are being built on the marsh, and then plus $2 million per mile times however many miles are being built on the dry land. So now if we come up to our diagram here, we've got to get from the bridge to the interchange, straight line from here to the edge of the marsh, another straight line from the edge of the marsh the rest of the way to the bridge. So I'm just going to kind of arbitrarily draw the first part of the highway like that. I emerge from the marsh right there, and then I'm going to have to draw another straight line the rest of the way to the interchange. So here's what I'm building on the marsh, here's what I'm building on the dry land. We want to pick this point to emerge from the marsh in order to minimize the cost of constructing this thing. So the distance that we're building on the marsh is whatever the length of this segment is, and the length that we're building on the dry land is whatever the length of this segment is. We can actually draw ourselves a little triangle right here, because we know that this is 4 miles to get from the bridge to the edge of the marsh, and we know that this is a full 10, so that's going to leave this dimension being 6. And so what we basically have here is we basically have these two right triangles. It'd be nice if we knew what the length of this leg was and what the length of this leg was, because if we did, we could just use the Pythagorean theorem to figure out what's going to go here and what's going to go here. And if you think about the question, it's at what point should the highway emerge from the marsh in order to minimize cost? We're trying to determine what this value is. So I'm going to assign that a variable x. And if I assign that a variable x, I know that x squared plus 4 squared has to equal this hypotenuse squared. Well, if I'm looking for an expression for the hypotenuse, it's going to be x squared plus 4 squared, but underneath a root to solve for the hypotenuse when you're using the Pythagorean theorem. So the distance that we're building on the marsh is going to be square root of x squared plus 16 miles. The distance that we're building on the dry land is going to involve something similar. It's going to be a little bit uglier because we don't want to introduce a new variable right here, because then our cost function would depend both on x and a different variable, whatever we assign for this dimension. We know it's a full 8 miles to get from the bridge horizontally over to the interchange. If we are saying that this is x miles of that full 8, we can say that the remaining distance is the full 8 minus the x that we've already traveled horizontally across the edge of the marsh there. If we use the Pythagorean theorem again, this squared plus this squared has got to equal the hypotenuse squared, taking the square root of 6 squared plus the other leg squared is going to give us the length of the highway that's going to be built on the dry land. So the distance that we're building on the dry land is going to be given by that root, so we'll just toss that here. And now what we typically try to do is we try to make sure this depends on a single variable. It already does. It only depends on x. We do like to have an interval if we can find one. There's no theoretical interval. The problem doesn't really specify that we have to emerge from the swamp at a point in between the bridge and the interchange. We could, and I'm going to erase this in a second, we could, build back this way and have x be negative and then build the rest of the way to the interchange, but there's no way that's going to minimize cost. We're building on the dry land way longer than we have to. We're also building on the marsh a little bit longer than we necessarily have to. So it's not necessarily going to be that. And we know that cost isn't going to be minimized if we build way over past where the interchange is and then build diagonally back to it. That's not going to minimize cost either. We're building on the marshland way longer than we have to. So the range of values for x should be somewhere between 0 and 8. And x could be 0, x could be 8. So I'm just going to throw this logical, not theoretical, but logical interval into the mix here. We should get a value in between 0 and 8 for x to give us our result. So once we're to this point, we want to know what values of x are critical numbers of this cost function. And so that's going to cause us to take the derivative of it. And when we take the derivative of this cost function, we're doing the derivative with respect to x. I'm thinking of this as x squared plus 16 to the 1/2 power. So I'm going to multiply by that 1/2 power and subtract 1 from it. So that'll be a negative 1/2 power. I'm going to have the same inner function sitting here. And then I have to use a chain rule, so I'm going to finish by multiplying by the derivative of this inner function. I'm going to add to that the derivative of this next piece. That's going to be another chain rule. And so I'm going to multiply this coefficient by a 1/2, right? A root is really a 1/2 power. So 2 times 1/2 is just 1. I'm going to subtract 1 from the 1/2, so that'll give me a negative 1/2 power. And then I'm going to have the same inner function I see sitting here inside of this quantity. And then I'm going to multiply by the derivative of this inner function. The derivative of 36 is 0. The derivative of this is actually going to require another little chain rule. So I'm going to do the derivative of the outer function, leave the inner function inside, multiply by the derivative of the inner function, and that chain rule is now done. So we get a pretty big, ugly looking derivative here. We can try to clean this up if we want to, but keep in mind what we're trying to do with this. We're trying to set this equal to 0. We're trying to figure out what the critical numbers of this cost function are. And so if we set this equal to 0, we can try to algebraically solve this for x, but what you're going to want to do when the calculator is involved, you're going to want to throw this thing into the calculator. So I'm just going to kind of carefully get this into the calculator here. And 5/2 is 2.5, so I'm just going to write 2.5 times, and grouping symbols are definitely going to make or break you here. I'm going to kind of do this so you can see me placing it into the calculator, because I'm guessing if you got to this point, if there's a mistake, it's going to be with inputting this to the calculator. I'm just going to write that power as negative 0.5 just because it's a little bit more efficient to get that into the calculator. And notice how that exponent is in a set of parentheses. And then I need to multiply that by this 2x right here. And then I'm going to add to that, let me move my calculator over so we can see the rest of this derivative. I'm going to add to that, I don't really need the 1, so I'm going to add to that a 36 plus, new set of parentheses. I need 8 minus x in that set of parentheses. I need to square that set of parentheses. I need to close that set of parentheses now. I need to raise to the negative 1/2 power again. I'm going to toss that power in parentheses. And then I need to multiply by this quantity, and I can definitely distribute some stuff if I wanted to have this go into the calculator a little bit more cleanly, but as long as you're careful, as long as you are putting a ton of parentheses in here around your exponents and wherever else you see them within your derivative, you should get to the proper graph. And if we go ahead and try to graph this now, standard viewing window should probably do the trick, because keep in mind where our answer has to come from. Our answer has to sit somewhere within this interval, and we can see that entire interval on the standard viewing window. And we do see that our cost function's derivative hits the x-axis right there, and we can definitely go ahead and use the calculator to figure out what that x is. So if we find that 0, we end up with an x value of 1.253 miles. So I'm just going to record that here. X is approximately 1.253 miles. Now we've got one of two ways to develop this conclusion, and depending on the wording in the problem, that'll kind of hint you as to what you are going to want to conclude with. The wording in this problem says, how much is saved over building the new highway in a straight line from the bridge to the interchange? That kind of implies that we need to know the minimum cost. Just to kind of save time, because I can only record a 15-minute video here, I'm going to conclude this with a sign chart. If you need to know the minimum cost, it makes more sense to say, well, the minimum cost is either going to happen here, here, or here. Let's fire all those values of x into our cost function. The smallest one gives us our minimum. But just for the purposes of wrapping up this video before I have to put an addendum onto it, we'll go ahead and just build our sign chart. So my x values have to sit between 0 and 8. The only time the sign of the derivative can change is as we cross the x value of 1.253. This is a graph of our derivative, and if we are looking to determine a sign chart for our derivative, we can just take the y values from this graph to help us fill that in. And the y values from this graph between 0 and 1.253 are definitely negative. So we're looking at a negative value for the derivative there. We're looking at a positive value, positive y value for the derivative on the remainder of that interval. And so that tells us that our cost has a negative rate of change, or is decreasing, between 0 and 1.253. It has a positive rate of change and is therefore increasing from 1.253 the rest of the way to 8. So which value of x is going to give you the minimum cost of installing this highway? Well, it's going to be, if you build the highway to emerge from the swamp 1.253 miles to the right of the bridge, because that's how we defined x. If I scroll back up to the diagram, x would be 1.25 miles to the right of the bridge. I know we haven't really answered everything that this question asked. The main thing that I wanted to make sure we emphasized here was finding the value of x that minimizes cost. We did do that. If we want the minimum cost, take that x value, toss it into your cost function in place of the x's, and boom, you've got your minimum cost.